Alright, hi everyone. So welcome to the second lesson of our topic 9 complex number in pure maths 3. So yeah, when we try to look at the learning outcome here, you would realize that the first learning outcome is the exactly same with the previous lesson, okay? Because there are some of the parts that we have mentioned, there are some of the parts that we bring it to this lesson. Yeah, so the thing that we are going to look at today is how to find the modulus and also the argument for a complex number, okay? So it will be helpful that you come back and read this after the lesson, because when you try to look at here, then you don't understand what is that actually mean. But you just remember we are going to look at the modulus and the argument of a complex number, and also how to represent a complex number by using an Argand diagram. Okay, then today we are going to look at another form of expressing a complex number, which is the polar form. Okay, so you'll be able to understand more about this. Then after that, we are going to carry out some operation for multiplication and division by using the polar form. Alright, so yeah, that's the main idea for this lesson, and it's going to be a longer lesson compared to a normal one. So yeah, please bear with me. Okay, so for the first thing, we are going to look at how do we represent a complex number geometrically by using an Argand diagram. Okay, so you know that for a real numbers, right, we can always represent the numbers by using a number line, right? So for example, if let's say you have the integer, like no matter it's positive, negative, then you can always represent, if let's say this is 0, then maybe this is like 2, then let's say this is like negative 2. So you'll be able to just represent all the number on this number line. So even it's what is that called, a fraction, then you'll be able to know that, like for example 1 over 2 will be somewhere here. Then you know that maybe negative 1 over 5 will be somewhere here. So even like an irrational number that, for example, like a pi, then you will know that it's like 3.142 blah blah. Then if let's say 3 is here, then you will know that pi is somewhere here. Okay, so all the real numbers, we can represent them by using a number line. But how about a complex number? So there's a problem about complex number is that we know that complex number is made up of two things, right? So the first one is the real part. Then after that, the second one, we have the imaginary part. So if let's say we are going to put them into a number line, also we'll have a problem that are we going to order them in terms of the real part or in terms of imaginary part? So that's why you can see that since the complex number is consisted of two parts, so for the representation, right, we also need to have two dimensions. So that's why we cannot use a number line to actually represent them, but we try to use a plan. Okay, so the complex number x plus iy can always be represented by the Cartesian plan. So it's something that's similar, like we have coordinate geometry, then you try to put them into coordinate, then you plot the plot. Okay, so we have x and y here. So you can see that the x actually represented the real part, then the y represent the imaginary part. Okay, so in the Argand diagram, the horizontal axis will be the real axis. Okay, and the vertical axis, in another hand, it will be the imaginary axis. Okay, so for example, right, let's say we have these two complex number. Okay, so there are two ways that we can always plot them. The first one is by using a plot form. So we try to let A be the point that represents Z1. So which means that what is the coordinate that we have? So the real come first, so that's why 2, 3. Okay, so if B represents Z2, then I'll have another point which is Z, which is 5, negative 3. Okay, so this is the horizontal axis, which represent the real part. Then this one represent the imaginary part. Okay, so when we try to plot, then we'll just follow the x and y, so which means A will be 2, 3. So 2, 3 is here. Okay, so this is the coordinate that represent this number. It's just like the same thing, like where is the 1 on the number line. So this is like where is 2 plus 3i in Argand diagram. Okay, so for the B, then it will be 5, negative 3. So it's like here. Alright, then the second type is we try to use a vector form. So by using a vector form, then the same thing, we will be doing the position vector. So like for example, OA, then I should have 2, 3. Okay, then if let's say I have a OB, so which means the OB will be 5, negative 3. So it's the exactly same thing like how you plot the point, but it's just that it's a vector now. So there's a line from OA, so this is A. Okay, then the same thing, you have 5, negative 3 here, so this is the vector for OB. All right, so the same thing, imaginary at the rear. Okay, so I guess this part should be quite easy. Yeah, because it's just the same thing like how you plot a normal coordinate. Okay, so this vector representation actually gives us another way to express the complex number, which is in a form of polar form. Okay, so before we move on to that part, then we'll need to understand what is that meant by polar coordinates first. Okay, so there are two concepts that we need to learn under this part, which is called as the modulus and also the argument. Okay, so the modulus of a complex number is exactly the same like how we find the magnitude of the position vector. So you see, just now we can actually represent a complex number in Argand diagram by using the vector form, right? So when we talk about the modulus of the complex number, it's exactly the same thing like we talk about the magnitude of the position vector. So that's why the modulus for the complex number z plus x plus iy, it will be equal to modulus z equal to square root x squared plus y squared. Okay, so the same thing, x will be like here, the real part, then after that y will be like your imaginary part, then magnitude will be referring to the length lah, so which is r in this form. Okay, then after that for the argument, so argument is the direction of the position vector. Okay, so but we are not going to express it in the form of the direction vector. So we are going to express it in the form of angle. So how do we write argument of complex x? It will be written as ARGZ. Okay, so and it's described as what is the angle between the positive real axis, and also the position vector. So later we are going to look at 4 different scenarios so you can see what is that mean by the area between the positive real axis. Okay, so the principal argument theta for a complex number is an angle such that it must be an angle that between negative pi and also pi. Okay, so you'll realize why is this got equal to, because when you say negative pi and pi, when we try to draw it, right? So this is the positive real axis. So you can imagine that from here to here is going to be pi. From here to here is going to be negative pi. So if let's say you are referring to this line, then we are always referring to pi rather than negative pi, because they are just the same line. So not to confuse. So that's why the angle must be a number between negative pi and pi. Or sometimes, if let's say it's given in a question that they want the angle to be in the form of 0 to 2 pi, then you can express it from 0 to 2 pi. But this is like the principal theta that we have. Okay, so how do we find the argument? Then we'll just use the basic for trigonometry. It's like the SOHCAHTOA that we tried to use before. So when you try to look at the question, then you'll find it very easy already. So this coordinate, which is written in the form of r theta, which your r is the modulus for the complex number, and the theta here is the argument of z, is called as the polar coordinate. Okay, so now we'll be looking at these 4 examples here. So to understand how do we find the modulus and argument. So A5 plus 12i, so to find the modulus, so I guess this part you should have no problem because it's just exactly the same like how you find the magnitude. So 5 square plus 12 square, which gives us the answer of 13. Okay, so for the argument, right, yeah, it's going to be the angle between the positive real axis and the position vector. So which means we can try to plot first. Okay, so which means it's going to be having this side and this side. So you can see since it's both positive, right, so you can try to imagine that this is the real and then this is the imaginary. So when you try to plot the position vector, then how is that going to look like? It's going to look like this, right? So this is like your 5, 12. So 5 is here, right? Then after that, this is going to be 12. Okay, so we want to find the angle between the positive real axis. So this is our positive real axis. So what is the angle between this line and the position vector? So which means that your theta, it should be here. Okay, so which means that I want to find this. So how can I do that? So you can try to plot a right angle triangle. So you have the height here, which is 12, and the length here is going to be 5. So that's why the argument for 5 plus 12z, sorry, 12i is going to be equal to, so t opposite and adjacent, right? So that's why shift tangent, then you have 12 and 5. Okay, so you can use your calculator to get your answer. Then after that, try to uh, round it to three significant figure. Okay, so 1.188 radian, so 3SF. Okay, so you can always try to check like whether the answer that you get right is like for example for this one it should be like a number that is less than half pi radian, so which means 1.18 is correct here. And normally for argument, right, we'll always express it in radian. We would not use degree. Make sure that you try to change your calculator to the mode of radian. Okay, so we try to look at the part B. Okay, negative 3 plus 4i. So same thing for the modulus. Yeah, you can try to do it by yourself. So square root negative 3 square plus 4 square. So the answer is 5. Okay, so for the argument, same thing. Let's try to draw it in the Argand diagram first. So which means the x will be negative 3, right? Then the y is positive 4. So which means we will have a position vector that look like this, where this is going to be negative 3 and this is 4. Okay, so you can try to write down the label here. So same thing, we try to draw the right angle triangle, but don't forget the argument, which is the angle that you wish to find, right? It's always must be the angle between the real axis, okay, the positive real axis to the position vector. So this is the theta that we want to find. So we can try to use this, but this will be our alpha lah. So which means it's like a reference for us to get the answer. So which means in this case, for me to get the argument for negative 3 plus 4i, which is the theta here, is going to be pi minus my alpha, right? Because the whole thing here is pi. So I need to minus the alpha, then only I can get my theta. Okay, so equal to, so for me to find my pi is going to be tangent negative 1. Okay, so the opposite is 4, then the adjacent is 3. Okay, so we are going to look at the length only. Yeah, so that's why it's going to be 4 over 3. Okay, so by using calculator, and you'll be able to get the radian and try to round it into three significant figures, so 2.21 radian. Okay, all right, so move on to C. Okay, 12 minus 5i, so same thing, start with magnitude. So we have 12 minus 5i square root 12 plus negative 5 square. So we have 13. Okay, so same thing. Let's try to draw the Argand diagram. So this one, you know that it's going to be like at the quadrant 4 there, because 12, then negative 5, right? So that's why your point is like somewhere here, which the x is going to be 12 and the y is going to be negative 5. So this is how the position vector look like. Okay, so same thing, when you have this, then which means that where is the argument, where is the angle that you are looking for? It's going to be from the positive real axis to the position vector. So this is the theta. So you might have a question that can you try to do the other way around? So which means like from here to here, because it's going to be from the positive real axis as well to the position vector, right? But for this part, we need to refer back to the principal argument that we mentioned just now. You remember the notes just now? We said that the theta will normally usually be expressed from negative pi and then to 2 pi. Sorry, and then to pi. Okay, so that's why we are trying to get it either if let's say it's in quadrant 1, 2, then we try to move from here. If let's say it's in quadrant 3, 4, then we try to move the other way around. Okay, I hope it explained. Okay, so same thing, we try to draw the right angle triangle here. All right, so opposite is 5, then the adjacent is 12. Okay, but this is the other way around, so which means that the argument, the theta that we are looking for is going to be equal to negative theta. Okay, because it's the other way, so this is the negative direction, right? So that's why negative, then tangent -1. So we are just treating it as 5 and 12. Okay, so opposite adjacent. So equal to, same thing by using your calculator and try to round it into 3 significant figure, 0.9. Okay, so just that. Alright, so move on to the last example here. So -4 minus -3i. So same thing, the modulus. Yeah, I guess this should be easy. So you should be able to get 5. Okay, so -4 and -3, which mean that when you try to draw the Argand diagram, it's going to be on the third quadrant. Yeah, so here is -4, then this will be the -3. So the point is here, then this is the position vector. So when you try to draw the right angle triangle, it will look like this. Yeah, so don't forget, we are going to look at from the real axis, from the positive real axis to the position vector. So this is the theta that we are looking for. But in our right angle triangle, the angle that we have is, we will try to denote it as alpha here. So which means for here, then the opposite is 4, then the adjacent is, I'm sorry, the opposite is 3, then the adjacent is 4. Okay, the length. Alright, so that's why to find this, our argument for -4 minus -3i will actually become, how do you find this? Yeah, so you can see from here to here is going to be -pi, right? Then after that, you deduct this part. So that's why it's going to be -pi then plus the alpha. Okay? Yeah, because like you move negative direction, right? So the whole thing you move up to here is -pi, then you plus this, then you come back, then you want to find this only. Okay, so -pi, then plus, so tangent -1. So opposite is 3, then 4. Alright, then after that we try to solve it. 2.498, blah blah blah. So try to change it to 3 significant figure, then we'll get our answer. Okay, so same thing, when you have this answer, then you should check that is that in this quadrant. So it's correct, right? Because it's more than half pi, then it's less than -pi. Okay, so that's the idea. Alright, so now let's try to look at the next part of the notes. Okay, so this is the main point of the lesson, which we try to express our complex number in polar form. Okay, so the real imaginary form x plus iy are actually called as the Cartesian form. Okay, so which means that when we try to represent in a diagram, right, we use the Cartesian coordinate. So like for example, if let's say we try to talk about the example 1a just now, right, which means when we try to draw it, then it will be in the Cartesian form, then we'll try to draw at the 5, then 12. Okay, then after that, when we try to draw it, then it will be somewhere here. So we know that this is 5 and this is 12, right? Okay, so this is actually in the Cartesian form. So, but after this, we are going to learn two different new forms to express a complex number. So it's called polar form. Alright, so what's the difference between polar form and Cartesian form? That is that polar form uses the polar coordinate. So polar coordinates, like what we mentioned just now in the notes previously, it actually means that we have a polar coordinates which consisted of r and theta. Okay, so the r is the magnitude, the modulus of the complex number, then the theta is the angle between the positive real axis and the position vector. So for example, from 1a, the answer that we found just now, right, we can get that the modulus is 13. then the angle, the argument is actually 1.18. So by using these two information, then I will be able to draw it on the Argand diagram. But it's just that I'm not using the 5 and 12. I'm just going to use these two, which means I know that for the position vector, the length will be 13. Then after that, the angle between the positive real axis and also the position vector that I draw, it will be 1.18. Okay, and the length from here to here is going to be 13. All right, I hope that you can like differentiate these two ideas. So that's why by using the polar form here, the polar coordinates, we will have two different forms of expressing complex number, which the first one we call as the modulus argument form. So which means that in the form that we try to express complex number, right, I do not have anything about the real part and the imaginary part anymore. I'm going to use the modulus and also the argument. Okay, so the same thing, then the other form is called as the exponential form. So we are going to look at this form one by one. Okay, so first we start with the modulus argument form. Okay, so let us try to derive the formula for the modulus argument form together. All right, so based on the explanation just now, so for modulus argument form, we are going to use the polar coordinate rather than the Cartesian coordinate. So that's why now we want to change the Cartesian form in a form of x equals to x plus iy, right? We are going to substitute the xy with another thing which consisted of the theta and r. So how are we going to do that? So this is a right angle triangle, right? So it means that I can always connect my x to my r and theta, right? And I can always connect my y and my r theta as well by using the SOHCAHTOA. So this is my angle, so which means this will be my opposite, my adjacent, and my hypotenuse. So which means that I can always connect x to theta and r by using cos. So that's why my cos will be equal to adjacent over hypotenuse, which is x over r. So in another words, x is equal to r cos theta. So we are going to do the same thing for the y. So it's going to be O and H, right? So that's why it's sine theta will be equal to y over r. So y will be equal to r sine theta. So now we already changed the xy into the form of r and theta. So now let us try to substitute. So we have z equals to x plus iy. So after we substitute, then we will get z equal to x is r cos theta, and then plus I, then y is r sine theta. All right, so now we have r and r, so which means that I can always write in r z equal to r and then cos theta minus I sine theta. So this is what we call as the modulus argument form, where z, what is z here? Z is basically our modulus, right? Okay, because this is the magnitude of the position vector. Then for the theta here will be our argument for z, because that is just the angle between the positive real axis and the position vector, so which is our argument. Okay, so now let us try out the example together. Okay, so u is 6 minus 3i, then w is negative 7 plus 5i. So write each of the complex number in modulus argument form. Okay, so the first thing that we need to find is to find the polar coordinate first. So which means we need to find the modulus and also to find the argument. All right, so let's try to do it for u first. So u equal to 6 minus 3i. So for the modulus part, it's going to be 6 squared plus negative 3 squared, okay, which will give us 45. And simplify, then we have 3 square root 5. All right, so now we continue to do the argument. So same thing, we can try to draw it. Okay, so 6 and then negative 3, so which means it's supposed to be at the quadrant 4. Okay, so this is all right, so this is going to be 6 and this is going to be negative 3. So let's try to draw the right angle triangle. So we have 6 here and 3 here. So this is our theta that we want to find. All right, and this is in the opposite direction, so that's why the argument for u is going to be negative theta. Okay, so the negative here, negative tangent, -1, so OA, so that's why 3/6. And we'll be able to get our answer negative 0.43464 in terms of three significant figure. Alright, so after we get this, then we are going to substitute into our formula just now. Alright, so so yeah, I'm just writing the formula for the first time maybe. So Z equal to R, then cos theta plus I sine theta, right? So we're just going to substitute the number inside. So Z will be U, okay? The complex number is U. Then our R is 3 square root 5. Okay, R is basically the modulus. Then theta is basically our argument. So that's why cos negative 0.464 and plus sine negative 0.464. Okay, so that will be our answer for this question. Okay, so let us move on to find the one for W. So W equals to negative 7 plus 5i. So same thing, find the modulus first. Okay, so after you get the modulus, then you can proceed to draw the Argand diagram. So for this one, it's going to be in this quadrant, I guess. Yeah. Okay, so negative 7 and 5. Alright, so right angle. So this will be our alpha, and the theta that we want to find supposed to be here. Alright, so which means here will be 5, then here will be 7. So our argument for W is equal to theta. So how can we find the theta here? Is by using pi, yeah, then minus the alpha. Okay, so which means pi minus shift tangent, so 5/7. Alright, so you can solve by using calculator and you will be able to get 2.5213 and so on, which after you round it off, then you'll be able to get 2.52 radian. Okay, so after we get this, then we can write it in the modulus argument form. So complex number W, the R, the modulus, so square root 674. Okay, so start from the cos. So we have cos, then 2.52. Okay, plus, don't forget the I, okay, then sine 2.52. Alright, so this will be our answer. Okay, so now we will proceed with the second form, which is the exponential form. Alright, so last time there's this mathematician named Euler discovered a relationship that states that cos theta plus I sine theta is equal to e to the power of I theta. And this relationship is actually called as the Euler's formula in mathematics. Euler's formula. Yeah. So the derivation for this formula is not included in your syllabus. So yeah, and I'm not going to spend like a lot of time to explain to you how do they get this formula, because it will involve a lot of theory that you didn't learn until now. So for example, like I think it involves things like power series as well. Yeah, so if you are interested, then you can try to Google it by yourself, but you'll realize that maybe there's a lot of steps in how they derive this formula you wouldn't be able to understand at this moment, and that's totally fine. Yeah, so what is important is we know how to apply this formula. Yeah, okay. So by using this Euler's formula, then it will be able to give us another representation of complex number, which called as the exponential form. So this is the second form that we mentioned under the polar form besides the modulus argument form. Okay, so from the modulus argument form, right, we would be able to know that Z is equal to R and then cos theta plus I sine theta, right? And since Euler's formula tells us that cos theta plus I sine theta is equal to e to the power of I theta, so which means that I can always write this, substitute the whole term here with e to the power of I theta, and it will give me another form of complex number which z is equal to r e to the power of I theta. Okay, where I is the same thing, which is the modulus for the complex number, and theta is the argument for the z. All right. Okay, so I'm just going to put in a quick summary here before we move on to to look at the next example. So basically in our complex number, which means in our syllabus here, a complex number will have three different forms. So for example here, right, for 1 plus I, and you have this and this. Actually, all these three different forms mean the same complex number. It's just that we try to express it in different form. So for the first one is the one that you can see the real part and then plus the imaginary part, right? So this is like the real and imaginary form. Then after that, the second one, which you can see cos and sine, then this is the modulus argument form, right? Then after that, the third one, which you can try to see the exponential, that is the one that we mentioned just now, which is called as the exponential form. Okay, so which means under the first one, right, the one that we are using the real part plus the imaginary part is actually under is actually using the coordinates under the Cartesian plan. So that's why this is called as the Cartesian form. Okay, which we will have the coordinate of x and y, right? Then after that, for these two, you can see that in the complex number itself, you cannot find anything like the real part, and you cannot find anything like the imaginary part. Of course, you have the I lah. What I mean is that you do not have the one that tell you one I, like the imaginary part is one. So in this, right, you have another two coordinate that you can see here, which is like the square root 2 and the pi over 4. So that's why for these two form, they are using the other coordinate, which is called as the polar coordinate. So that's why these two form is called as the polar formula. So for polar form, they are using polar coordinates, which the x part is actually the r. Then after that, you have the argument part for your y. Okay, so in the next example, we'll be able to see like how do we actually change all the different form by using different information given. All right, so let's go to number 3. All right, A. So write the given complex number in a form given here. So A z1 equal to 1 plus I. So you are given the Cartesian form, then you are required to write in the modulus argument form and the exponential form. Okay, so you can see that this question is exactly the same with the example that I put in here. So which means later when we try to find out the answer, then we should be able to get this exact same value. Yeah. Okay, so now let's try to do it. Yeah, so I guess this is easy because the modulus argument form is the one that we have tried just now. So which means the first thing that we need to find is always start with the modulus and the argument first. All right, so for this question, then we can write down the modulus first. So the modulus for z, it will be equal to 1 square plus 1 square. So it will give us square root 2. Okay, then after that, we can continue with the argument. So for this one, it will be in the first quadrant. Okay, so I1 and then 1. All right, so this is our theta, so which is our argument here. So which means our argument for Z1, it will be equal to tangent -1 and then 1 over 1, right? Okay, then after you solve it, then you will be able to get pi over 4. All right, so now let's try to write our answer. So which means the modulus form is going to be the modulus. So Z1 will be equal to R is the modulus. Okay, then after that cos pi over 4, then plus I sine pi over 4. Okay, so just like that. So this is the modulus argument form. Then for the exponential form, it's going to be z2. It's also z1 here. Sorry, my mistake. z1 equal to, yeah, so what is my r is square root 2, right? Then after that e, then to the power of I theta. So my theta here is pi over 4, so that's why pi over 4i, and that's it. All right, so which means you can see 1, 2, they are just using like the same coordinate which in the polar form. Then by using the formula, then you would be able to get your answer already. Okay, so now let's look at B. So you can see that the given form is in the form of exponential. So we need to write in the modulus argument form, then we continue to find the Cartesian form. So you can imagine that for the first one, it will be easy because by using this, right, then we would be able to identify the modulus already. So which means the modulus for Z2 is actually equal to 5, right? Then after that, the argument for Z2 is actually pi over 3. Okay, by having these two, then we can find the modulus argument form already. So which means Z2 will be equal to our R is 5. Okay, then after that bracket cos pi over 3 and then plus I sine pi over 3. Yeah, so the one that is more tricky is the Cartesian form. So how are you going to change this one back into the Cartesian form? Okay, so the first thing is we also need to try to draw it. Sorry for the sound. Okay, yeah, so by using this, then we can always try to identify where is our position vector. So since this is pi over 3, right? So pi over 3, you can imagine it's like less than half pi. So that's why this will be under my first quadrant as well. Because if let's say it's in quadrant 3, 4, then it's going to be negative. So if let's say it's quadrant 2, then it's going to be a number that's between half pi and pi. So that's why pi over 3, which means the position vector is like somewhere like this. Because this only can give us pi over 3, right? Then after that, we have the magnitude here, which is the modulus, like the length of this position vector is going to be 5. So the problem here is we need to find what is our this one, what is our x here and what is our y here, right? So how can we do that? Same thing by using SOHCAHTOA as well. So we have one angle, then we have the r here, so which means we can find the x and y. So let's start with cos maybe. So cos pi over 3 will be equal to AH, right? So x over 5. So which means that x will be equal to 5 cos pi over 3, which gives us 5 over 2. Okay, then the same thing, sine pi over 3 will be equal to y over 5, right? So O over H. So y is equal to 5 sine pi over 3, which will give me 5 square root 3 over 2. Okay, so after you get this, then which means that you know that what is the length here. So both is going to be a positive number, so which means we doesn't need to do any changes there. So which means that for number 2, our Cartesian form, yeah, so just writing down. Okay, so the Cartesian form will actually equal to Z2 will be equal to the x is 5 over 2 and then plus 5 square root 3 over 2i. Okay, so actually this thing you can straight away do it by using your calculator as well. So let's try to do it. So maybe we use it to check whether our answer is correct or not. Alright, so let's try to use our calculator to check our answer. So we can check it from the modulus argument form by just putting the value in the calculator and check whether we get this or not. So which means that 5 cos pi over 3. So 5 cos, then after that pi over 3. Okay, it should give us the exact same value 5 over 2. So as you can see. Yeah, so after that you have I sine pi over 3, right? And don't forget you will expand the 5 as well. So which means that it's going to be 5, then after that is sine now, so pi over 3 as well. So you can see 5, then pi square root 3 over 2i as well. Okay, so that's why for the modulus and argument form, you can always check it by using your calculator. Alright, so let's try to move on to the next question. Okay, so for, sorry, this is supposed to be C. I'll try to change it in your handout. Okay, so Z3 equal to cos negative pi over 4 plus I sine negative pi over 4. Yeah, so this is in the form of the modulus argument form. Then we need to write it in exponential. So for our first one, it's going to be easy because by looking at this, then we should able to realize that our r here, yeah, okay, our r or the modulus for z3 is basically 1 lah, because you do not have any number before that, right? So the r is 1. Okay, then after that, the angle, so which means the argument for z3, it will be equal to negative pi over 4. So by using these two information, then we will be able to write the exponential form. So which means z3 will be equal to r is 1, so no need to write. So e to the power of negative pi over 4, 1. Sorry, I. Okay, so now we proceed to 2, so which means we need to do the Cartesian form now. So same thing, so we need to identify where is our position vector. All right, so we have negative pi over 4, right? So which means the angle will be the negative direction. So that's why it's going to be like in the quadrant 4. Okay, because if negative pi over 4, then it wouldn't be, it is not a number that is larger than negative pi over 2. So that's why it should be like somewhere here only. Okay, and this is pi over 4. And we know that the radian, the r here is 1. Okay, so the same thing now, we need to find out what is our x and what is our y. And don't forget your y here, it should be a negative y. Okay, so which means when we try to get the x and y, we will actually get it in a positive number. Then after that, we need to, based on our coordinate here, then we try to change it to negative. Okay, so that's why same thing, we start with the cos. So cos pi over 4 is equal to a over h, so x over 1. So which means x is equal to square root 2 over 2. Okay, then we have sine pi over 4 is equal to y over 1. And don't forget, this one is negative 1, right? So you can just try to put it here. So later your answer will have negative. So y will be equal to negative square root 2 over 2. Okay, so you must make sure your y is a negative number. If not, then it's going to be wrong already. All right, okay, so now we have our x and y already, so which means our Cartesian form will be z3 equal to square root 2 and then minus square root 2 over 2i. So when you try to check it, then you know that x is in a positive, then your y is negative, so which means the answer is correct. So same thing, you can always try to use your calculator to check your answer as well for this question. Okay, so let's move on to number 4. Okay, number 4. So given u is equal to 5e to the power of 2i and w is 10e to the power of negative 3i. So A, find u, w, and w over u. Okay, so yeah, this is the form to show to you that in terms of multiplication and division, it is very helpful for us to use exponential form. So later we'll be looking this in a more deeper way when we try to talk about the last section of the notes. Okay, so we have uw, which means it's going to be complex number u multiply complex number w, right? So uw will be equal to 5e 2i and then multiply 10e to the power of negative 3i. Okay, so this is multiplication, so that's why it's going to be 5 multiply 10, so you get 50. So this is exponential form, right? So we know that, for example, if let's say we have am multiplied with an, then it's going to be a, then the power plus together. So it's the same thing here as well. So that's why e, then 2i plus minus plus negative 3i. So that's why uw will be equal to 50e to the power of negative I. Okay, so after that, let's check on w over u. So w over u is going to be 10e negative 3i over 5e 2i. So same thing here. So 10 divided by 5, then we'll be able to get 2. So this is divide. So 10m divide an, it will be equal to am minus n, right? So the power minus. So negative 3i minus 2i. So from here, then I will be able to get my answer 2e negative 5i. Okay, but you have a problem here is that you remember just now, our theta, our argument, right, it should be always in the interval from negative pi until pi only. So negative pi, which means it's like negative 3.142 and so on, right? So negative 5 is obviously out of this range already. So how are we going to do that? So we need to find out what is the principal value that represented by the negative 5 here. So that's why the negative 5 is less than negative pi. Okay, so that's why we can try to draw it and see how negative 5 look like. So this is our, yeah, so you can imagine, so half is like negative 3.14, sorry, the one, meaning that pi, it will be negative 3.142, right? So pi over 2 is something like 1.57. So you can imagine this is like negative 1.57. Okay, then you have negative 3.14. Okay, so when you move on, then you plus another half pi, then you will be able to get like negative 4.72. So this come back, then it will be like negative pi already lah. So negative pi, sorry, negative 2 pi. So you can imagine negative 5 is going to be like somewhere here, right? So which means it reach here. So which means for me to find the argument for the same position vector is going to be here, right? So how can I find here? Then which means that I can get the 5 here, then I use 2 pi to minus 5, then I will be able to get the theta that I want. So that's why the theta will be equal to 2 pi minus 5. Okay, you don't need to do minus 5, right? Because from here to here is going to be like an angle of 5 radian. So for you to find this part, then you are just going to use the whole circle, which is 2 pi to minus 5 lah. So for here, you will be able to get like 1.28, okay, radian, which is in 3 significant figure. So we can write W over U is equal to 2E 1.28 I. Alright, yeah, so you must always make sure that the argument that you try to put, right, is something that within your range. So later we'll be having one more question that's similar like this as well. Okay, so now let's move on to the part B. Alright, so show UW, 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 and also W over U on a single Argand diagram. Okay, so let me just try to copy down the information so we can go faster. Okay, so there are actually two ways that you can try to do this. So the first one is obviously you can actually check out the, what is that called, the angle here, the argument, and also the radius. Then you can decide like how long the line is and how the, what is that called, the angle will look like. So for example, if let's say this is my diagram, right? So I will have things like this. Okay, so what I can expect is for the first one, my argument here is 2. So which means that it's going to be like more than half pi already. Then after that, the radius is like 5. So which means that I can have it like somewhere here. So this is like a sketch. So if let's say this is U lah, then I try to state that this is going to be my A. Okay, so which means this is going to be 5, and then from here to here is going to be like 2 radian. Alright, then the same thing for W, then the magnitude is going to be 10, then after that it's negative 3. So negative 3, then it will be in the quadrant 3. So that's why negative 3. So it's almost going to be negative pi already, so it should be like nearer. And the magnitude will be 10, so maybe it will be further a bit. So this is going to be my B, so which is the W here. So which means from here to here is going to be the negative 3. Okay, so this is like a sketch. Then after that, UW, so it's negative 1, so which means it's somewhere here. Then after that is 50, so that's why this should be the one that is like the longest lah. So that's why this will be my C. Then from here to here is going to be negative 1. So for the last one, W over U is going to be 2 pi minus 5. So from just now, what we get is 1.28. I'm just writing the whole thing here because later I want to show you the other calculation. So 1.28, then it's almost half here as well. Okay, so here to here is at 1.28. Then after that, the magnitude here, it should be only 2, so it should be shortest. So maybe it's somewhere here. Okay, so this is D because the magnitude is 2. Okay, so how can we prove that this thing is actually correct? Because if we try to sketch it like this, right, it will be a little bit difficult because we doesn't know how the exact angle look like, right? So which means that if we try to show it in a much more accurate way, then which means we might need to write it in the modulus argument form. Then after that, we try to change it back to Cartesian form. So which means like for the first one, I have the r here. So which means when I try to write it in modulus argument form, right, then I have 5, then cos 2 plus I sine 2. Okay, so by using this, then we can try to check with our calculator. So 5 cos 2 will give us negative 2.08. Okay, and then plus, so 5 sine 2 will give us positive 4.55i. Okay, so we do not need to be like very accurate, but the idea is like A is almost negative 2 and 5 lah. Yeah, so when you try to compare to this, which means it's okay, right? Because it's like negative 2 then 5, so which means it's in quadrant 2, so it's a correct one. So the same thing we can try to check with W, then you will have like 10, then after that cos negative 3, right? Then plus I sine negative 3. So you can track it with calculator as well. 10 cos negative 3, it will give you negative 9.90. Then after that, 10 sine negative 3, it will give you negative 1.41i. Okay, so by using this, then we'll be able to get our coordinate as well. So which means it's roughly going to be like negative 10 and then negative 1. Yeah, so which means it's like somewhere here lah. So it's in the third quadrant, so which means it's correct because negative x and negative y, right? So it's the same thing for like UW. You can try to check it out. So I think for this one, you'll be able to get the C is roughly 27 and negative 42. So which means it's correct as well. So positive x, then negative 42. And it should be the furthest right because compared to all this, then this is 27 and negative 42. Okay, so when I try to check the last one, then your D, it will be around 1 over 2 and 2. So which means it's correct that D is in the first quadrant, then is the nearest one to the origin. Yeah, so this is the idea how you can show everything in a single Argand diagram. Okay, so yeah, after this, we move on to the last part of the lesson, which we try to talk about the multiplication and division in a much more detailed way. Okay, so last part we are going to talk about the multiplication and the division of two complex number expressed in the polar form. Okay, so actually we have tried this before with the example 4 that we have previously. Yeah, but we are going to talk about how do we find the modulus and the argument now. Alright, so yeah, let Z1 be this and this is Z2. So both of them are in the form of the exponential form. Okay, so we need to find the Z1, Z2. Okay, so which means it's going to be multiplication here. So R1 E I theta 1 multiply with R2 E I theta 2. Okay, so after we solve it, then we will get our answer R1, R2, then E I theta 1 is going to plus, right? Plus the index that we have. So let's try to simplify. So we have R1, R2. So we do some factorizing here. So it's the I, then theta 1 plus theta 2. Okay, so now by using this term, then we need to identify what is the modulus. What is the modulus for Z1, Z2? So which means now our complex number becomes Z1, Z2 already, right? So the modulus eventually will be equal to R1, R2, right? Yeah, I hope that you can see the idea. Let me try to draw this. So which means now this will be our complex number, right? The whole thing here. So the whole thing here, when we try to compare with our normal, so Z is equal to R e power I theta. So that's why the R here is our modulus. So which means the whole thing here is going to be the modulus for Z1, Z2. Then after that, I theta. So that's why now this is my new theta. So that's why the theta 1 plus theta 2 is going to be the argument for my Z1, Z2. Okay, so yeah, that's the idea. So now let's continue. So we have Z1, R1, R2. So which means how do we get R1, R2? It's basically the modulus for Z1 and the modulus for Z2. Alright, so the idea is if let's say we want to find the modulus for Z1 multiplied with Z2 without doing the operation of this, we can straight away take the modulus that multiply them together. Alright, so now let's try to look at the argument. So the argument for Z1, Z2, so just now we mentioned already, is going to be like theta 1 plus theta 2, right? So what is theta 1, what is theta 2? Yeah, so theta 1 is basically the argument for my Z1. Then the theta 2 is the argument for my Z2. So which means if I want to find the argument for the complex number Z1 multiply Z2, I can straight away use my argument for Z1 and plus my argument for Z2. Okay, so later we are going to apply this in our example 5. Okay, so same thing, let's proceed with the division here. So now we want to do Z1 divided by Z2. So Z1 divided by Z2. So what do we have? So we have R1 EI theta 1 over R2 EI theta 2. Okay, so since this is divide, so that's why it's going to be minus. So R2 divide R1. Then after that, I theta 1 minus I theta 2. So same thing, we try to do factorization. So R2 over R1 will be equal to EI, then theta 1 minus theta 2. Okay, so it's the same thing like what we did just now. So normal Z will be equal to R then EI theta, right? So that's why now my complex number becomes Z1 over Z2 already. Then after that, my R here become R2 over R1. Then my theta here is theta 1 minus theta 2. So that's why the modulus for Z1 over Z2 is going to be equal to R2 over R1. So which in another words is basically the modulus itself divided by the modulus. Okay, then when we try to do the argument, so same thing, Z1 over Z2. Alright, so for the argument is theta 1 minus theta 2, right? Yeah, so that's why it's going to be argument for Z1 minus the argument for Z2. Okay, so what we can remember is that for multiplication, for us to find the modulus for the multiplication between the complex number, we multiply the modulus together. Then if it's divide, then we divide the modulus. So for us to find the argument, then which means we will try to plus the two arguments together. For divide, then we will minus the two arguments. Alright, so now we proceed to example 5, then you would understand the idea better. Okay, so the complex number u and w are given that u equals to 9 plus 12i, then w is -5 minus 3i. So find the modulus and argument of u, w, and u over w. Alright, so which means that how are we going to do that? We need to find out what is the modulus and also the argument for each u and w first. Okay, so let's start with u. So u is equal to 9 plus 12i. So modulus u is square root 9 plus 12, so which will give us 15. Okay, so same thing, when we try to draw this, then it will be on the first quadrant. So this is our 9, then this will be 12, and this is our theta. So argument for u is equal to shift tangent 12 over 9. Okay, which is, we try to write the answer with more significant figure first, because later we are going to plus them together, then we need to use more than 3 except later. Okay, so this is my u. So now we proceed with our w. So equal to -5 minus 3i. So modulus for w. Okay, so I will get 34. So same thing, So negative, negative, so it should be in here. All right, so here. So this will be my alpha again lah. So this is the data that I want to find. So this is 5 and this is 3. Okay, so my argument u will be equal to same thing. This is going to be negative pi and then plus shift negative 1 and OA 3 over 5. Okay, so when we solve it, then we'll be able to get negative 2.601593 and so on. So in 3SF, that is negative 2.60 radian. Okay, so we are going to use this result to help us to find the modulus and the argument for this. So the idea of doing this is we actually do not need to find the u and w in the terms of exponential. Then after that, we expand and we see the number. We only use the result that we get just now. So which means if for multiply, right? So let's try to start with A. Okay, so for UW, then we find the modulus first. So for UW, is going to be exactly the same when we try to use the modulus of U to multiply the modulus of W. So that's the idea of using the result just now. So the modulus of U is 15, then the modulus for W is 34. So this will be my answer. Okay, then after that, I want to find the argument for UW. So remember, for the multiply one for argument, then we need to plus that. So it's the argument for U and then plus the argument for W. Okay, so this is a case where I mentioned we might need to write more decimal place because to make sure that our answer is accurate enough. So you can just write, yeah, depends on you, like how long you want to write. So yeah, but make sure it's more than 3 SF lah. So yeah. So you can use your calculator and you'll be able to get your answer in 3SF. So 39, sorry, this is negative. So negative as well. Okay, so negative 1.67 radian in 3SF. Okay, so I hope that by now you'll be able to see how important the result just now, because if not, which means that you are going to like expand the UW, then after that you find the modulus for, you need to find the modulus again by using the exponential form and so on. Yeah, so that's why this help us to ease the whole process. Okay, so the same thing, then we proceed to the B. Okay, so the first part is U over W, right? Alright, so for divide, then it's going to be divide as well. So modulus U over modulus V, sorry, or modulus U over modulus W. Okay, so what we have here is 15 over square root 34. Alright, so just try to rationalize it. So we are able to get our answer 15 square root 34 over 34. Okay, then after that, for the next one, so argument for U over W. Yeah, so for argument just now, it's minus, right? So argument U minus the argument for W. So equal to, so you can write for SF. Yeah, I'm just writing like for SF here. So minus, then minus 2.6016. Okay, then you will be able to get your answer 3.5289 radian. Okay, so why am I writing this long? Because you'll realize that 3.5 is more than your pi again. So you remember the range just now. So this number shouldn't be more than 3.142 blah blah blah. So that's why we need to check what is the value of this again. So which means this is my normal. Yeah, so starting from my positive, right? So which means the angle is from here to here. So it's like roughly here, which is my 3.5289. So which means for the angle to go back to the range of the principal argument, then I'll need to find what is the angle here, right? So how can I find it? Yeah, so the whole thing is going to be negative 2 pi. So I plus another 3.5289 lah. So which means for me to get the theta, it will be equal to negative 2 pi plus 3.5289. It's no problem as well if let's say you you cannot think of like negative 2 pi then plus this, which means you can just do 2 pi minus this, then you negative your answer. You are just getting the exactly same thing. So writing in 3SF, so 2, 5, then radian 3SF. Okay, so which means this will be my last answer for my argument U over W. Alright, so I hope that you can understand from the result just now. Alright, so now let's proceed with example 6. Alright, so this is the same idea as number 5. So that's why I'm going to fast forward the working here. So yeah, please try to go through by yourself. Then after that, come back to check your answer. Okay, or you can just let it run. Then after that, you check your answer lah. Alright, so let's start. Alright, so I hope that you are able to answer the question just now and remember to check your answer. So I'm just going to close this video by doing a very quick recap on the learning outcome of today. Yeah, so at the first part of the lesson, we learned about the modulus and the argument, right? So basically, this is the part that we mentioned just now in the notes. So which means normally the argument will be referring to angle theta, which is in between negative pi to pi. So in some cases, maybe they will request for theta between 0 to 2 pi, but given in the questions. Yeah, so normally I will still prefer you to write it by using the principal argument, which is in the form of negative pi to pi. Okay, after that, we also know how to represent the complex number by using the Argand diagram. So no matter it's the one that by using point or by using the vector when we try to find the polar form. Okay, so the last thing, then we know how to express the complex number in the form of polar form, right? So we have the modulus argument form, then we have the exponential form. Okay, then we also understand for the last part when we talk about the operation for multiplication and division, then we get the result of, if let's say you want to find the modulus between the multiplication of two complex number, then we can straight away use the modulus to multiply. And if let's say we try to find the argument for multiplication, then we can plus the two individual argument together. So if let's say it's division, then it's going to be divide for modulus, then minus for argument. All right, so this is like the whole idea for this lesson. All right, so yeah, so please remember to just understand everything, then spend some time to finish your homework. All right, so that's it for today's session. Thank you.